All right, this is a class, as you may have guessed, on heat transfer. So what does it mean? Right, what is heat? Think first about what is this definition? What is heat? Well, heat's kind of this ambiguous concept. Right? It's not a thing. It's an effect. It's something that comes about because it's due to the movement of energy. Right? Heat is just the movement of energy. So heat, as we define it here, is a transfer of energy. And it always is due to a temperature gradient. Right? If you have a body that's sitting there and it's a uniform temperature, there's not going to be any heat flow within that body because there's no reason for heat to move. Right? There's no temperature gradient. Okay. What are the mechanisms? Like this is all recap, hopefully for you guys. Right? So with the mechanisms of heat transfer, right? We have conduction. Right? This is where we're going to spend probably the first quarter of the class or so on conduction. It's structured pretty similar to 364. So conduction is, think of it as a movement within a body, some domain, movement of energy due to like vibration or transport of electrons or sort of things that are happening within a fixed body. Right? Radiation, on the other hand, is something that happens at a distance, right? This is something that's happening between two bodies that are at some distance, and there could be matter between them or not. It could be like the sun to the earth, right? There is no matter, there's a vacuum between those things. It's still exchanging heat, and that's due to radiation. So intuitively, I think conduction kind of makes sense when you really think about it. It's kind of easy to picture what conduction is. You have these little molecules and they're vibrating and passing that energy on within a body. Radiation is maybe a little bit less intuitive, but it's really just the release of photons, right? Or the release of electromagnetic energy that propagates through space and hits something else, okay? The last thing here, which I'll kind of tentatively call 3, right? The last thing, it's not really its own thing, it's convection. Convection is really just conduction. It's just conduction where you have a body sitting there and on the other side of it, you have a fluid. The heat's conducting into the fluid's moving, and then you get sort of different effects because of that. Okay, so like I said, conduction, we're first going to be focusing on this. This is energy transfer related to interactions on the microscale, right? Microscale energy carriers within a material. This could be, like I said, electrons moving in a substance. It could be vibrations of energy within the molecules or atoms, and they're propagating along. Whatever the case, it's a very local phenomenon. How do we describe conduction? Every time we have conduction, we pull out something called Fourier's law. Fourier's law. Okay, Fourier's law. Who remembers what that says? It says Q dot, which we're going to use our nomenclature. Q dot is heat transfer. So the units on Q dot are usually watts, right? Fourier's law can be expressed in terms of the heat flow per unit area. So heat flow would be watts per meter squared. And we would denote that Q dot double prime. Right, so the heat flux, watts per meter squared, is equal to minus K times the partial derivative of T with respect to some direction, right? So let's say we have a Cartesian coordinate system, we'll call it X to begin with. All right, so the heat flux in the X direction, which we'll denote here, we'll add a little X, is given by this equation. So if you know the temperature gradient in the X direction, just look at the temperature gradient in the X direction, multiply that by minus the conductivity of the material, that's going to give you your heat flux. Okay, relatively simple. Fourier's law can also be written in the other dimensions, right? We could write it in y, and it would just be minus k dt dy, or we could write it equivalently for the z direction, right? And that's the same thing, right? But ultimately, we know that Fourier's law has to come out of these microscale energy carriers that are within a material. So maybe it would help us to understand conduction and where Fourier's law comes from. Like this is just a model. Right? Fourier's law is just a model of what's happening. So where does it actually come from? How do we go from the microscale to this continuum model, this thing that we observe at the continuum level? Okay, so let's kind of walk through a little bit of that. Sorry, catch up with my notes here. Okay, so let's sketch out maybe some examples. So let's take, I'm going to make some axes here, and we're going to have, on this axis, we're going to have temperature. Oops. Temperature, and then on this axis, we're going to have position. Right? And again, by the way, if you ever can't read what I'm not the best handwriter, especially on an iPad, but if you can't read what I'm saying, just interrupt me. Read what I'm writing, just interrupt me. Okay, so let's say we've got some plane wall just being an infinite wall that's sort of, of finite thickness, but of infinite dimension. Now let's say we have a temperature profile within that wall, and that temperature profile might look like something like this, right? Temperature is a function of position. So let's take some virtual wall, some kind of virtual plane here. And let's say that we're going to observe what's happening at that very faint gray dotted line. Let's sort of go down to the microscale and look at what's happening there. Well, you might see at the microscale that there would be some movement of energy carriers across this plane. Okay, we'll just call that Q dot in the positive X direction. You would see electrons moving in the positive direction. You'd see vibrations of energy that sort of propagate in the positive direction. Whatever the microscale energy carrier is, you're going to see that there's movement across that plane. Okay, you'd also see not just movement in one direction, you'd see movement in the other direction as well. Q dot X minus. You'd still see electrons moving. There's sort of chaos at that level. There's randomness in the movement. Right? You're seeing things that are moving both ways. So we have both heat flow in the positive X direction and heat flow in the negative X direction at the microscale. Okay. But what we want to think about is actually there's kind of the way that we arrive at Fourier's law. So let's draw this. I'm going to draw this boundary here. Hopefully get that straight. Okay, so let's imagine that there's a length. Okay, this length here, this is the same length despite my bad drawing. And we'll call this length LMS. LMS. Okay, LMS is the microscale length. Let me just make a note here. So LMS. Okay, so LMS is the distance between microscale MS energy carrier interactions. Right? What do I mean by that? So like, let's imagine that you're in a lattice structure. Right? You're an atom in a lattice structure. That lattice structure is going to be have a distance between interactions, kind of on the order of whatever the periodicity of that lattice is. Right? If you have molecules over here, atoms over here, and you're over here, the closest that you could interact is that gap between it. Right? That would be LMS. It's kind of the order of magnitude of the length at which these microscale interactions happen. So if you're right in that plane wall, that infinitely kind of small plane wall, you're looking one direction to the X minus and one direction to the X plus, and you're going to see there's this distance where kind of the average effect or the average interaction is happening. Okay, this distance is really important to understanding where Fourier's law comes from. Okay, but before we can decide how actually we get to Fourier's law, we need to decide that that distance is small enough. Okay, there's something called the Conduction number. Conduction number. Okay, Kn. So Kn is kind of like the BO number, but it's a measure of the fraction of the microscale length at which the energy interactions are happening to some characteristic length for the problem. Okay, so if I'm looking at a body, and that body is relatively big, like it's continuum big, and the interactions are happening on the molecular level, clearly LMS is much smaller than L characteristic. L characteristic would be like the size of this block that I'm looking at, right? Clearly, it's less than 1. then in that case, when it's much less than 1, then we can say Fourier's law is appropriate. If you're in a situation, however, where maybe there's is a near vacuum situation, or is it like a rarefied gas? You have matter there. The interactions are happening, but the interactions are on a very large time scale or a space scale compared to the overall problem, where maybe this Knudsen number starts to approach 1 or goes above 1. In those situations, Fourier's law doesn't work anymore, right? Fourier's law as a model of what's happening in heat transfer is not appropriate. Okay, first we need to convince ourselves LMS is much smaller than L characteristic. When we have that, then we can make some, then the following analysis that we're going to do is valid. Okay, so let's just assume that this is the case, that Knudsen number is much less than 1 and we're okay. All right, then we can move on. So let's see, let's write out what we think, so some expressions for these Q dots. So, all right, let's first take Q dot in the x plus direction. So what could we write that gives us Q dot in the x plus direction? Well, this is approximately, just kind of conceptually defining it this way. Q dot is the number of energy carriers. Think of this, okay, electrons, or the number of, the frequency of vibrations, phonons, or whatever it is. Electrons are kind of a helpful way of thinking about it. So number of energy carriers per second that are crossing this boundary. And then in order to get heat flux out of this, or heat flow out of it, we need to know the energy per carrier. Okay, so number of carriers per second, energy per carrier, we end up with energy per second, right? Watts, that's what we want. Okay, we can write this a slightly different way, break it down a little bit more, and say the same thing, but we're now just in terms of number of carriers per unit volume. Right, so the carrier density times the area that it's crossing, times the velocity at which it's crossing on average, times the carrier heat capacity, okay, times the temperature of the material. And so we've broken down our really simple number of carriers per second, energy per carrier, into a little bit more detail, right? Carrier density, velocity, heat capacity, and the temperature of the material. Okay, so now, let's just write it this way. So let's give some symbols for these things. Okay, Q dot x plus approximately equal to n ms times area times v ms c ms times t. Okay, but now before we can decide what we're doing with this temperature, what is this temperature? We need to think about where the interactions are happening immediately before the energy carriers move across this boundary. All right, so looking over here, we're at this boundary here. Where is it? So if we have heat flowing in the positive x direction, where is the interaction going to happen immediately before they cross over? Okay, we're going to be moving, the interaction's happening here at our LMS, and the energy carrier moves in this direction, right? And we end up crossing over the boundary. Okay, so this temperature is the temperature at x equals x minus LMS, okay, where we say that this position here is x, the plane's position is x. All right, so Q in the x plus direction is at x equals x minus LMS. We can write the same equation for what's happening for heat flux that's going in the negative x direction, right? So you just write it out the same way. Qx minus is approximately equal to the same things. Just say, copy that. But it's at Tx equals x plus LMS, right? Now the net heat transfer like this is great. We've got x plus, x minus, but this is not ultimately what we want. Right? We don't care about the microscale. We care about the continuum scale. So we actually want the net heat transfer. Right? The net heat transfer is just Q dot equals Q dot x. Let's see, Q dot x plus, right? Minus Q dot x minus. And what's going in the positive x direction minus what's going in the minus x direction. Okay, we write that out, and it would just be Q dot in the x direction net is equal to n ms times A times V ms times C ms times T in the x minus x LMS minus TX x, sorry, clearly TX equals x plus LMS. Okay, just make sure I got that. Okay, this is fine, but how does this help us? Right? Remember, we're trying to get to Fourier's law. The whole point of this discussion is how do we go from the microscale to something in Fourier's law? Does this really look like Fourier's law? Remember what Fourier's law says, it's Q dot x equals minus K partial T partial x. Not really. I mean, you can kind of, like there's a temperature in there, sure, there's some stuff multiplying temperature, but it's not really that close. So what are some things we can do to make this look more like Fourier's law? Any questions before I move on to that? Okay. All right, so moving on. So this is what we just, up here at the top is what we just derived, hopefully. It's a little small. So how do we make this look, this equation up here, how do we make this look a little bit more like Fourier's law? Okay, well, first thing we can do is let's try to get rid of that area, right? There's no area in Fourier's law as we wrote it, so we'll say Q dot double prime is equal to, right, this is our Q dot, so we'll just say Q dot divided by A. We're just going to divide by that area. Okay, that helps a little bit. We end up with NMS times C MS, oops, times V, missed that, times V MS times our temperatures. Tx equals x minus x minus LMS minus T x equals x plus LMS. Okay, incremental step, it helped a little bit. Remember, we're trying to get to Q dot equals minus K dt dx. That's our goal. The next step is the critical one, and that's, let's remember what the definition of a derivative is. Right? Think back to your calculus class, and when you took a derivative, what were you actually doing? Like, what's the actual definition of what we're doing? Okay, so let's write out for a temperature derivative with respect to x. What is the sort of calculus definition of this? Right, it is, we have a temperature difference, right? So on the top we have dt, or partial t. So we need a temperature difference. It's x equals x plus dx, let's say, minus tx equals x minus dx. Okay, so we have some temperature difference. And then in the denominator, we have a distance, right? We're taking dt dx, so the temperature, d distance. So what's the distance between these two temperatures? 2 times dx, right? But really what we want here is the limit, right? We want the limit as dx goes to 0. This is a definition of the derivative dt dx. Okay, this is a separate observation from what we've been doing, but we can use this. And I do want to point out here, just note this x plus dx appears first here, okay, where x minus LMS appears first up here. Okay, so there's some sort of subtle differences here. Okay, well, let's try to use this. So let's make our heat flux equation look more like this derivative. So what we can do is we're going to say Q dot double prime is approximately equal to, let's multiply and divide by the distance so that we're multiplying by 1 effectively, but we can get distance in the denominator. Okay, so we end up with our distance here is 2 times LMS times NMS, VMS, CMS times the temperature difference, T, x equals x minus LMS, x equals x plus LMS, divided by our distance, and our distance was 2 LMS, right? We just basically multiplied by 2 LMS over 2 LMS. Okay, but now this is starting to look a little bit more like Fourier's law. And you can probably see where this is all going to end up. So if we take this equation and we take the limit as LMS goes to 0, right? When our Knudsen number is small enough, LMS basically goes to 0. Then we end up with Q dot double prime is equal to, so remember the sign has to flip because our definition of the derivative was inverse. So we have now minus LMS times NMS times VMS times CMS times the partial. Okay. This now looks a lot more like Fourier's law. Except, what are we saying? We're saying this out here is basically our conductivity. This is basically our material's conductivity. And if you think about it, it actually kind of makes sense, right? You have a microscale length, the number of microscale energy carriers, the velocity, and the specific heat capacity. And if you think about changing any of those things, you can see how, yeah, you have a bigger length, right? So if the length at which they're interacting grows, all things else equal, then that means the heat can move more quickly. The interactions are happening spatially more quickly. Your conductivity goes up. More energy carriers, higher density, right? All those things are going to lead to higher conductivity. Yeah. Yeah, right. So I should add in here again, approximately. Okay. And then if I want to really weasel out of it, I'll just say K is proportional to these things, right? Not exactly equal to. Good point, though. Okay, so let's look at conductivity, and this really will wrap up our discussion of where Fourier's law comes from. So here's a plot. Right here we show our plot of different materials. Let me just kind of zoom in a little bit. So down here we've got temperature, right, as a function of temperature, and then we have thermal conductivity. So up here, right, look, we've at the really high side of this plot, we've got things like high purity copper, high purity aluminum, right? And then at the bottom, the very bad conductivities, we have things like air, Teflon, right? So what are some themes that we can draw out of this that relate to what we just talked about? Well, let's say you have high purity copper. What do we know about high purity metals? They've got a lot of electrons, a lot of free electrons. They can move really freely. It's a pure substance, so there's not impurities sitting in the way that impede the progress of the electrons as they're moving. Okay, so those high purity metals actually are really good thermal conductors in addition to being good electrical conductors. As you go down the list here, you start seeing alloy. Right? Alloy is by design it is designed to have impurities in it. So now you are introducing impedance to movement of electrons, which are the primary heat carrier. Go all the way down to things like air. Okay, now you have really big gaps between molecules, and they don't really move that quickly, so low conductivity. Or things like Teflon. Okay, it's a relatively dense substance, it's solid, but there are no free electrons, right? The organic molecules that are involved don't have a lot of free electrons, so the only way that Teflon can transmit heat is by vibration, right? And that is a slow way to transmit heat, right? So this is just kind of a conceptual way, and it maybe helps understand a little bit of where this stuff all comes from.